Okay, let's take a look at today's lesson. We're going to be doing parametric equations day 2 today. Today's lesson is going to involve a calculator, so hopefully you have one with you and you can kind of go along with me with the calculator. We're going to be looking at the different modes that the calculator has. We actually are going to be using the parametric mode today. So let's go ahead and pull the calculator up. If you would look at your mode button. So notice that here we have different options for function, parametric, polar, sequences. We have 4 different modes. If you look at this button right here, see how there are 4 different variables on there? Each variable, so the x goes with function mode, the t goes with parametric mode, see the theta goes with polar mode, and the n goes with sequence mode. You don't have to change the variable. The calculator automatically does that for you. So when you press this button, you're going to get whichever variable whose mode you're in. All right, you don't have to change it to a capital T. It's going to be there already. So we need to be sure we're in parametric mode, and we also need to be sure we're in radians, because if you're in degrees, it's not going to graph it properly. So we need parametric and we need radians. Okay. The other thing we want to look at is the window, and we're going to be graphing some trig functions. So I'm going to change it from 0 to 2 pi. Okay, my step is a little bit larger. Actually, y'all are at like at 0.13 or something like that. Aren't you? Isn't standards like 0.13? I'll just change it to 0.13. And my x min, I want to bring that down to like -3 and 3, because this is going to be kind of a small graph, right? It's just sine and cosine. And my y min, I want to go like -3 to 3, just so we can get a better picture. Okay, so that's adjusting my window. So we have 3 variables to adjust for, the t and the x and the y. Are we okay with that? So now I'm just going to go and input the first set of equations. Move this over a little bit. So sine 2t. So see how it automatically gives me an x and a y? That's because I'm in parametric mode. I didn't do anything except switch it into parametric mode. So here for the x equation, I'm going to put sine 2t, and notice it just gives me a t automatically because I am in parametric mode. And then for y, we need to put 2 cosine t. Okay? And now we're going to graph it. So it kind of looks like a figure 8, which is kind of cool, I think. It's kind of cool. So to sketch that graph, and we don't need to be really perfectly accurate, just notice that this is out like 1 space and 2 spaces, so we just need a roundabout sketch of it. So it looks like it comes up to the top. And there's a sketch for us. I mean, that's really all I'm looking for is a sketch like that. Okay? We okay with that? All right, let's do the second one. All right, so the second one was, let's just look at my sheet. So sine 3t. So let's go back to y equals. We need sine 3t. And then 2 cosine, the y is the same, so let's graph that one. Wow. Okay, so there's that one. If we want it to go slower, and we are going to want our next one to go slower, all we have to do is go into our window and change our t-step. What this is doing, this t-steps, is telling your calculator every interval. What is the interval that you want me to plot a point or calculate a value? Every 0.13 time I'm going to calculate a value. If I change that to smaller, my calculator has to calculate more values, right? So it's going to take it longer to graph. And so if you want the graph to move slower, you would just change your t-step. Now I guess the downside of that is that if you make this t-step too large, then you won't get a good picture of the graph, right? Say you made it a 1. You only wanted 1 point for every 1. You wouldn't really get a good graph, would you? So you just need to keep that in mind if you're going to be messing with it. How it really affects is it changes the number of data points that the calculator is calculating for you. That's what it does. Okay, so just and if you get it all messed up, just reset your RAM and it'll put it back to default, and you don't have to worry about it if it gets messed up. All right, so that is graphing this one. So let's sketch that graph. Looks like we still have 2 up and 2 down and 1 to the side, but we have an extra little curve. Okay, and that's all I'm looking for a sketch, just a little sketch. All right, so how are we doing on our calculators? We okay with the mode and all that? Okay. So we have a couple of problems on the next page that we're going to be using a calculator for. So let's go to our next page. So this first problem, okay, so I call it the Gary problem. It's kind of fun. So here's what we're going to do. Gary walks along a horizontal line. This is important. He's going back and forth on a horizontal line. There is no Y movement at all. It's just X movement, walking back and forth on a horizontal line. And the coordinates of his position in meters, so we have some units, are given by this. So this is it says S of t, that's his position, but in parametrics, that's going to be our x equal equation, right? Because he's going horizontal, he's walking horizontally. The y equal equation is really whatever we want it to be, because it's just going to be a matter of positioning it on the screen for us, right? So it's going to be back and forth movement. If you have a calculator that's not color, you really wouldn't want your y value to be 0. How would we see it on the x-axis, right? There's already a line there. This is going to be a line that's going back and forth. So I'm going to make my y value like 2. I mean, that's fine, 2. So we make a y value of 2. Notice that I have a specific amount of time that I'm looking at, 0 to 12. So I'm setting up the components of what we need to write in our calculator. All right, so we're supposed to use parametric equations to simulate the motion. We're supposed to describe the motion, how far does he travel, what's his displacement, and please add to this, what's his average speed. So add that on your notes, what's his average speed? So we're going to calculate his average speed as well. So let's go to our calculators and let's get this all set up so we can see what's going on. Alright, so I'm going to go to my window. My time, I have to go from 0 to 12 because that's what they said. I don't get to pick. Okay, it said 0 to 12. And I'm going to keep it at a 0.07 because I want it to slow down a bit, because I want to be looking at this horizontal movement going back and forth. Okay? Now, the X min and max, I remember that it's a fairly wide range that he's moving. So I'm going to change, and if you didn't know, you just have to go back in and adjust. You know, I would go -15 to 15. I think that will, you know, find all the movement. My Y min and Y max, basically I'm going to have him at 2. Right, so my Y min could be 0. I mean, we don't really need to see the negative ones. And since I'm going to have him at 2, why don't we just put the Y max at a 4? I mean, just so we can see him a little bit better. So any questions on setting the window? This is just for our convenience so that we can see what's going on. Okay, so I set my time by what they said, and then my X, trying to get the whole movement. If you can't, you have to go back in and adjust it. All right, so let's go to our Y equals. And let's enter Gary's equation. Okay, so for my Y, I'm just going to put it at 2, right? You can put it anywhere you want. It just allows you to see the movement. Keeping it at 0 on the x-axis really just is harder to see because there's a whole line there already. So let's type in his horizontal movement equation. So that's -0.1 times, then we have t cubed. Notice I just push that and I get a t cubed, and then we have minus 20 t squared, then we have plus 110 t, and then we have minus 85. Now, what we should really do to be able to see what's going on is go over here to the left of your x equals. So move over here. Come on, move over here. Slow, slow. There we go. All right, so I'm going to hit enter. So if you have a colored calculator, it will look like this. If you don't, you're just going to get this line options. So I'm going to go to the line options. And I really want this thing right here. I call it the chaser. I don't know what you want to call it, but it's like a little 0 with a little dash by it. You want to select that. You want the little chaser. And so you hit enter and then enter. And then let's graph Gary and see what happens. Okay, so left, right, left. I just need to know direction. When this is saying right over here, it says describe the motion. Then I'm just going to write in there. Come on. So the motion was, we'll just put it here. Left, then right, then left. That's answering the question, describe the motion. I just need direction. I don't need anything else. Left, right, and then left. Okay, how far does he travel? What's his displacement? Now that's more specific. So let's talk about how we would do that. Now this is going to be an estimate. Okay, then we're all going to need to estimate the same way. In calculus, we can find the exact amount that he traveled. We're not going to get that precise. We're just going to do an estimate. So what I want you to do is I want you to go into your table set. So let's go to our table set. So second window is our table set. We're going to start this at 0, at time of 0, because that's where we start, right? Is everybody okay? And I want you to put your change in table as a 0.1. That's what we need, is a 0.1. We all need to do a 0.1 so that we all have the same estimates. If you put something different in there, you're going to get a different estimate than the rest of us. Please don't do that. We all want to estimate with a 0.1. So what we're going to do is we're going to follow his path from the table. That's what we're going to do. We're going to follow his path from the table. So I'm going to go to the table, second graph, and see that he starts at a position of 8.5. Right? When time is 0, he's at 8.5. So I'm going to work on the first left. Right? I'm working on my directions. So he started at 8.5. And now what I'm going to have to do, and yes, you have to scroll. I know we're so used to having things happen so fast. Just relax and scroll. Okay. Relax and scroll. We're going to scroll. We're going to scroll down. See, he's going to 8, 7, 6. See how he's going left? 5, 4. We need to scroll until he turns. And we're just going to have to scroll until we see him turn. So we're going to go over here, and we're just going to scroll down. Okay, see he's going -1, -2, -3, -4, -6, -7, -8, -9. Let's see. There we go. Here we go. See in here he's going -9.7, 9.8, 9.8, 9.9, and then he turns around. We're just going to the tenths. We're just going to round to the tenths every time. Don't keep the thousandths in. We're not worried about accuracy. This is just a rough estimate. So he goes left until position of -9.9. Okay, so he was at 8.5 with the x on the x-axis, then he moved to -9.9. So now he's going to start moving right. He's going to start at -9.9. Right, that's where he's starting. He's starting where he ended. And let's just keep scrolling. Okay, let's keep scrolling down. So he's going right, -9, -8, -7, -6, -5, 4. We'll just keep going. 3, 2, 1. Oh, there we go. So right here, he goes -1.4, 1.3, 1.2, 1.2, and then he's switching back around to 1.3. Okay, we're just going to go to the tenths. So he goes as far as -1.2. Okay, that's as far as he goes right. So on the last leg, he's going left again. He starts at negative 1.2, and we just really need to go to 12, right? Because the time is to 12. So we're going to just scroll down to 12, because, I mean, that's the end of the time, and see where he ends up. Okay, so at 12, he ends up at negative 8.3. Now, the reason that I've done this is because we have to determine what his distance, how far has he traveled. And our distance is going to be, I have to do the distance of each individual leg, right? Because we have positive and negative motion. We can't do it all together. So the distance, and this is critical here, the distance is going to be the absolute value of end minus beginning. Absolute value of end minus beginning. Absolute value of negative 9.9 minus 8.5. That is my distance. Okay, and so we calculate that and we get 18.4. So he traveled 18.4 meters on the first left leg. I did my end position minus my beginning position, because that's how you do distance. End minus beginning. That's absolute value. So let's do how far did he go when he did the right, when he was moving right? Well, end was negative 1.2 minus a negative 9.9. So when he was on that right leg, he went 8.7 meters. Okay, I did end minus beginning, the absolute value of that, because it's a distance. And the last leg, when he turned around, he went left again. We do absolute value of end, which is negative 8.3 minus beginning. Oops. Negative 1.2, and that gives me 7.3 meters. So I add all those distances up, and Gary traveled 34.4 meters. That was his distance. So I'm going to pause there for a second. Are we okay with that? So I just calculated each. We have to calculate them separately. We cannot do them together. Okay? Now for displacement, displacement takes negative into account. Let's remind ourselves what displacement is. So I can be standing right here and move right 5 steps and left 5 steps and end up right where I am. My displacement would be 0. My distance would be 10, but my displacement would be 0, right? It's a concept. It's basically how far are you from where you started. And the way we calculate that is the very end minus the very beginning. That's what displacement is. So let's do our displacement, and it is not absolute valued because displacement has a direction. So the end, he ended at negative 8.3 minus, end minus beginning is our formula, end minus beginning. Our beginning was 8.5. So his displacement was negative 16.8 meters. What does it mean that the displacement is negative? That means he's left of where he started, right? He's left of where he started. That's what it means. What if it had been positive? That would mean he's right of where he started. It's a location. Okay? And the very last thing we're going to calculate is the average speed. In order to do the average speed, we need the formula. Let's go over here. So distance equals rate times time. Remember that formula from junior high. Distance equals rate times time. It's an oldie but a goodie. We use it all the time. The distance, he traveled 34.4. We don't know the rate. That's what we're solving for. How long was he traveling? 12 seconds or minutes. It doesn't really tell us. It should, but it doesn't tell us the actual unit of time. So to find the rate, I would simply solve for r. So it's going to be 34.4 divided by 12. Or the rate that he traveled was 2.867 meters per whatever the unit of time is. So this would be my average, or his average speed. And that's the Gary problem. How are we with that? It's a lot, isn't it? Yeah, it's a big process. So just know that I'm not going to give you a problem where you have to investigate the time length of 24. It's going to be 12 or smaller. I'm not going to give you anything bigger than 12 to investigate. Okay? All right, so we have one more question to look at. So let's take a look at our spider and fly question. Okay, go away. There we go. All right. So we have a spider and a fly crawl, so their positions at time t in seconds are, now some students earlier were having trouble with this. Okay, this is the vector form of a parametric. I told you they were very closely related. I'm going to rewrite this as a parametric so that you can see it a little bit better. Do you have to rewrite it? No, but I'm going to show you how. What you do is you match up. So x is going to equal -2 plus 1 times t. So x equals -2 plus t. Okay, y equals, I matched the second pieces up. Y equals 5, and then 2 times -t is -2t. These are my parametric equations for the spider. It's just a different way to write them, that's all. And we need to be comfortable going back and forth between those two modes. So this is the spider. Okay. And the t-chart for the spider, let's go ahead and do a t-chart because we're going to graph it. I'm just going to go from time 0 to 1. Again, I think we've done enough t-charts. I'm just going to copy that in. So the spider is at -2, 5 when he starts, then goes to -1, 3, then goes to 0, 1. So this is the spider. So now let's translate the fly's equations into parametrics just so that we get some practice. Okay, so x would be 1 minus t, and y would be 1 plus t. I'm just taking it off of here. We seeing how that works? We're just taking the first position and making that x. The second position is y. So let's do a t-chart for the fly. Oops. X and y. So 0, 1, 2. We're going to do the same 0, 1, 2. So for the fly, starts out at 1, 1, then goes to 0, 2, goes to -1, 3. Okay, so we're asked to make a sketch showing their paths at different times. So that's what we're going to do. Okay, so let's do the spider first. The spider starts at -2, 5, right here, and then moves to -1, 3, and then moves to 0, 1. Okay, so that's the path of the spider. Let's change the color of the fly. So the fly is at 1, 1, and then moves to 0, 2, and then goes to 1, 3. Okay, so that's the fly, and that's the spider. Alright, so now let's answer questions about that. So do their lines of travel meet? Yes. At -1, 3. Do we see that? They cross at -1, 3. Do they meet at the same time? Justify. Well, it's kind of hard to see from the graph. Why don't we look at our table? We know they meet at their paths cross at -1, 3. The fly gets to -1, 3 at 2. What are we in? Seconds? 2 seconds. The spider gets there at 1 second. Are they at the same place at the same time? No. No. And what we do to justify is we describe where they are. So the spider is there at t equals 1. The fly is there at t equals 2. so they don't actually meet, their paths just cross. Okay? How is that?